Today for this talk we have John Tantalo. He is a Case grad who works at Google now. We'll be talking about Google Maps and WebGL. So, yeah, I'll let him go.
Do you guys know who I am? I'd like to get to know who you are. How many people are undergraduates? How many people graduated to Case? Not many. Cool. Any professors? Yep. One professor? Any grad students? No grad students? I'm grad student. You're grad student. Good. Good day. So I'm John. I work at Google. I did an internship at Google when I was at Case, back in the old days. And I just started working at Google again over the summer. And I work at Google in Seattle, not Google. And I work on Google Maps, which is based primarily in Seattle. And so today's talk is going to be about, it's going to start with Google Geo and a little bit of the history, and then the rest of the talk will be about Google in general. I suppose no one has any questions before I get started. Okay. So I'm going to start with a demo of the kind of the project that I'm working on, which is MapsGL. Does anyone use MapsGL? Does anyone know what it is? Can you tell me what it is?
MapsGL is a project to make your maps graphics accelerated by your graphics card.
That's right. So MapsGL is a project to port basically Google Maps in the browser to OpenGL, which in the browser is implemented as a technology called WebGL. WebGL is basically a subset of OpenGL designed for the browser, designed for JavaScript, that allows hardware accelerated 3D graphics in the browser. We launched it last October, I think, so it's been out for about a year now. And we're going to see if we can't do... So the way you get to it is actually when you go to Google Maps is this experience MapsGL down here. And I think if you click that, it like runs a test in your browser to see if it works. Because not every browser supports it. So let's do some demos. Here we go. Experience MapsGL. So this may look like the Google Maps you know and love. Raise your hand if you've used MapsGL. So a couple people have. I just want to show in case not everyone's seen it. So MapsGL is a lot like regular Google Maps, except transitioning between zooms is noticeably different because labels kind of they will blur in and out, and they should like slide into position rather than in old Google Maps kind of just like pop from one zoom level to the other. That's one of the big differences. You can kind of see that labels will fade in and out between zooms. So this is all happening, all this is being rendered on the client side by the graphics processor running this Mac. And a couple of the other cool things you can see is if I go to Chrome, where we have a lot of cool buildings. Zoom out a little bit. So this is just regular satellite imagery, and this is the oblique 45-degree imagery. And we have different angles that you can switch between. So all this is happening client side. And that's kind of it. So and WebGL, I'll talk a little bit about that. It's available for, so we've got IE, Firefox, and Chrome over here. This is the current support for it. So Chrome supports it back a couple of versions. IE doesn't support it, but between Safari, I think that's Safari, and Firefox, they have marginal support for it. And something like 52% of users have a browser that can support WebGL. So you might be asking, like, why did we do this? Why did we take Google Maps, which seemed to be working just fine, and make it work in WebGL? The answer is because we wanted it to be better and a lot more fluid. And the second reason is because we want to advance the browser technology to be able to do new things in the browser. WebGL is interesting because it's, well, we want to be able to do high-performance graphics in the browser, and the only way to do that is to use the GPU, but before now there hasn't been a way to do any sort of 3D graphics in the browser. So we kind of had this problem where we want to be able to do 3D graphics in the browser, but there's not very good support, and we kind of want to add support for it, but there's no applications that are using it. So it's kind of this chicken and egg problem where there's no good support because there's no applications, and no applications because there's no good support. So Google Maps was one of the first large projects to use WebGL. So that we kind of became the first client and started pushing browser support to improve, and especially in Chrome. So, you know, Google Maps and Google Chrome teams work very closely together to try to advance the WebGL standard, to improve support in the browser, to find bugs, to add features that weren't there before. So they started improving their support for WebGL, and we started adding new features in the client, and everyone was happy, so we got WebGL improving and MapsGL improving at the same time. So now other clients, not other clients, but other applications that want to use WebGL, they can kind of follow in our footsteps and use the technology that we've helped develop and we've helped inspire the Chrome team to add to. So we feel like contributing to the sort of browser ecosystem by making WebGL a really useful technology has helped make the web better. But the main reason we wanted to do this was to make Google Maps better. So you all remember, like 2005 back then, Google Maps came on the scene. And what was the big difference between Google Maps and the map applications before that?
Move it around.
They were cool.
It was cool?
I immediately had people telling me, a friend of mine said, "You've got to see this."
You could pan without it having to like load, I think, MapQuest, like had you click little buttons to switch the pane over.
Yeah.
So you could just click and go.
So yeah, you could click and drag and move the map around anywhere you want. You could zoom in and out without reloading the page. So I think the thing that a lot of people took away from Google Maps was Ajax, and that's where the term first started coming into prominence. Does anyone know what Ajax means? I'm sure. Does anyone not know what Ajax means? That's better. You don't know what it means? It means asynchronous JavaScript over XML HTTP requests. So it basically means making requests from the browser to a server without reloading the page. And in Google Maps, they did that to fetch tiles or to do driving directions. Like that. At first, it was just tiles, and then they added satellite view, and they added driving directions. But so it's still like that, you know. Google Maps today is, you know, still just tiles. They're images, they're downloaded from the server, and that's what it was back in 2005 or 2007, and we're trying to break that barrier and try to do something new with Google Maps, and that's what MapsGL is trying to do. So the main thing we wanted to add to Google Maps was something we call fluidity. And fluidity has this concept of seamless maps, dynamic maps, fast maps, and svelte maps. So what we mean by seamless is transitioning between different views of the map, like from the map view to satellite view, or down to street view, or even to photo montages or anything you might want to do next to the map will be a smooth transition between those two things. So when you're actually controlling the client in the browser, when you're drawing the map in the browser, it's much easier to make those kinds of transitions rather than if you're having to go from tiles to go from something else. So by having much more control over that client, we can make those maps much more seamless and transition between different elements. Dynamic maps, and this is very important. Let's step back a second. Does anyone know what the difference is between a raster image and a vector image? Does everyone know the difference? Does anyone not know the difference? So I think the main thing about having dynamic maps, what I mean by this is when we render maps in the client, they're vector maps. They're not rasters. So we are sending down geometry that includes roads, where roads are, where buildings are, and also includes the styles of those roads, the styles of buildings, so what color they should be painted with, the thickness of lines. When we render in the client, if we want to change the rendering at any time, change the color of roads in response to users' actions, like getting driving directions, that means instead of sending down new tiles, we can just change the color. And we have all the geometry we already need. We don't need to download new geometry, we don't need to download new tiles, don't need to download anything really. Just tell the client to change the color. We can render 3D buildings with parallax. Let me show a demo of that. I don't think we saw that. Let's go to my folder.
If only there was a mapping tool.
Oh. Over here. There. Do you see how the buildings are changing from the angle of the perspective? So these maps aren't, each tile is not rendered and then served as an image up into this presentation. These are being rendered in real time. So as you pan around, the buildings are changing their perspective. So this is a completely dynamic map. We can change this at any time, and the shadows on the buildings will even change by the time of day, and the latitude and longitude. So that should be the correct shadow for that building right now. These maps are much faster because we're using the GPU to render these maps. It's not happening in the client, and it's not happening in the browser. These maps are being packaged up and delivered to the client, already in a format, ready to go into the GPU. They've already been tesselated down to triangles, and the shaders have been pre-computed. These are ready to go straight into the GPU. There's not much that has to happen on the client before they can go to the hardware. And last, they're much smaller. These map tiles are much smaller than the raster images. And the reason for that is because, does anyone have a cell phone? Mobile clients need to work on much smaller amounts of data because they have a lot more limited bandwidth. So Google Maps for mobile introduced this problem of how do we get a really great maps experience into the mobile phone with a much more limited device. And the way they were able to solve that was switching from raster maps to vector maps, because you can fit a lot more information into a vector image than you can into a raster image. So this is kind of the state of the art for mobile. This is Google Maps on an Android device, and these are all rendered as vectors. And you can kind of see that because the buildings have parallax and they're nicely transparent. So the impetus behind MapsGL, it sort of was born out of Google Maps for mobile, where we developed these clients for rendering 3D maps in mobile phones. We had this technology on the server side to deliver vector maps to the clients the next step was to develop a vector client for the web browser. Does that make sense? So that was the sort of the series, and this project I think went live in 2009 and WebGL last year. So let's talk a little bit of Maps technology. We are slaves to the GPU. We tell the GPU what to do, but it's the one doing all the heavy lifting for us. The GPU. It is a very particular device. It doesn't want to do a lot of things. It does want to render triangles, and a lot of them very quickly. It does not want to do lines. No, it doesn't understand lines. It doesn't know anything about text. And it's not great at anti-aliasing. It has a lot of anti-aliasing, you can do anti-aliasing with the GPU, but it is one of the more difficult things to do. So it doesn't know anything about lines, doesn't know text. It turns out in Google Maps we do lots of lines and text. This is not like Doom. This isn't Quake 3. There's no particles. There's no smoke effects. It doesn't seem like the kind of thing you would do with a GPU. But it works. You can pretty much do anything you want with a GPU. And it took a lot of work, but we were able to get pretty much the same Google Maps experience as you would see in the raster client, in the vector client. So this is my office, by the way. I look on this canal, and we see the ships going by all the time. So we do lots of lines, lots of text, and it has to be anti-aliased, because we need to have it needs to be pretty. Google Maps has always been pretty. I think that was one of the major differentiating features between Google Maps and earlier versions of mapping in the web, is that everything was pretty. We're not satisfied putting up something that doesn't look nice. So the question then becomes, how do you make the GPU understand this type of illustration? How do you tell it what to do here? So this is an example of how that last scene would be presented to the GPU. Each of these elements is a different fragment that we send to the fragment shader. I'm not going to get too deep into GPU stuff because I don't know much about it. I'm really not a GPU, OpenGL, WebGL guy. I'm really a JavaScript programmer. But these are the elements that we send to the hardware. And you can see, in some cases we do get triangles. Like all the water and all the backgrounds, green stuff, gray stuff. That's the green stuff, that's the gray stuff. They are rendered they're sent down from the server as tessellated geometry, just a bunch of triangles. You can see where we have tile boundaries here. This is like the corner of the tile. So they are sent down as tiles. Here's one tile, and then each tile will have 1,700 polygons in it. Each polygon has a bunch of triangles. We have labels, so each label is a different fragment. And so you can kind of get an idea of the density of the information from just this one image. And so, how do we actually do the rendering is the next one. Go ahead.
Can you flip that?
Yeah.
So the labels there, so one of the magic things I always love about Google Maps and these map interfaces is that the labels are shown proportionally to the zoom effectively. Is there information like a weighting or something that's associated with the labels?
I believe, yeah, I don't know firsthand.
Okay.
Because I haven't used or interacted with that layer of the map myself. But I do believe that they are weighted, and that they have to be laid out in an algorithm. Like I think it's kind of a stochastic algorithm. Really. Okay. We kind of like put them on the map and I kind of jiggle them around until they get to the right place. And different labels will outweigh other labels. And so when two of them collide, one of them will obliterate the other.
Okay.
And there's actually a ton of research in this area. It's a very active research field.
Thanks.
Just putting labels on a map. So how do we go from this, which is just sort of like where stuff goes, to pixels? Because this doesn't tell us what pixels to put on the screen. This is what we're going for in the end. So smooth lines, anti-aliasing, And so that's what we're going to talk about next. How do we actually draw this scene in terms of the graphics processing? So curvy, bendy, fat lines, they've got thickness, they've got outlines. Every line is outlines, and the outline has to actually go all the way around the edge of the road. You notice outlines actually go over other things. So this road with its outline goes underneath this road with its outline. So in the GPU, it's actually, we get a little help because the GPU, when you're sending geometry to a GPU, you send it with depth. So we can actually tell the GPU that this thing is over this thing, and it knows, it understands that concept of depth. But we still render roads in multiple passes because we have to render, the road and its outline. So we usually will render an outline and the road on top of it, and then the outline and then the road on top of it. So it's multiple different passes for the roads. And there's also multiple passes that have to happen for curves. So we can draw the line segment as just like a little rectangle. But we can't really, where the rectangle bends to do a curve, it's hard to fill in that gap. So you can see that there are little notches missing. So this is just the segments of the rows. So we have one shader that just draws segments. And we have another one that does the joins. I'll go to this. And this is all the little joins. So when we draw that road, we're drawing the road, which is just this big fat guy. All those get drawn first, and then we draw the joins like circles like this. So this is an illustration of all the joins that would happen in that map. So there's the segments, and there's all the joins that happen between each line segment. And these are all drawn with circles with different radius and different outlines and different colors. But all this can be computed in the graphics hardware, so we're not computing this in the JavaScript client. And then they're simply composited together, and that's the finished result. That looks pretty good. Smooth roads with rounded corners, and everything is layer present. Now, this is what it looks like in the raster maps. When you zoom in really close, the maps are nice and smooth, the anti-aliased. So this is kind of this is what we're aiming for. Because this is all done with a software-based anti-aliasing on the server. So this is considered perfect. We would like to have something a lot like this. Now when you just use, if we were to just output our maps from the GPU as we give it to them, this is what you would see. Very hard lines, and our users would be really upset by this because it's not beautiful and it's not nice to look at. I think it's pretty hard to look at. And it doesn't really add to the impression that Google Maps are high quality, which is what we're going for. So this is what we want to add. So we have a couple different methods of anti-aliasing that we've tried, and depending on the graphics hardware in your machine, we fall back to one or the other. So this is multi-sample anti-aliasing, which is something that is common in OpenGL applications, and we can implement it in WebGL. The way this works, though, is at each boundary where a point kind of lies on the edge of a triangle, the point can sample the depth and the color values that it's supposed to have. Like it can interpolate them from somewhere onto the triangle. So if it's coloring, if the triangle's like here, it's coloring a pixel like here, and the point's like off the pixel somewhere, or off the triangle, it can like interpolate like where it's supposed to be and use those color values. And this is a pretty efficient way of getting anti-aliasing, but it's not as pretty. You can see this is a lot more smooth, I think, than multi-sample anti-aliasing. And a much more simple way is to just render everything at twice the size. You know, so 4 times as much drawing actually happens, 4 times as much memory, and just scale it down. That's what super sampling is. So we're drawing everything, you know, we're drawing every pixel, basically 4 pixels, and then scaling it down to 1 pixel. Or another way, in other words, we're kind of sampling each pixel 4 times and computing a mean of that color value and using that to read that pixel. Does that make sense? So those are the 2 different types of anti-aliasing, and depending on the GPU, depending on the browser, we'll use one or the other. And this is sort of the fallback because this is a lot easier to do. It's much less involved with the. I think multi-sample anti-aliasing is actually it uses a lot more of the GPU. I mean, it uses features that are developed that are native or not to the graphics card. And we can do super sampling with pretty much any graphics card, so that's why this is the fallback. But it's much more expensive to do for every frame because, you know, we're basically doing 4 times as much drawing. So in most cases that's fine. Like if you're just looking at a map, it's that's not that we can do super sampling because it's not much is happening other than just drawing. But if we're also panning, maybe loading other tiles, or doing layout for labels, we might turn off super sampling. So like the on and then off, and then on and then off. But it may not be happening in this client, but that's an example of something you could do. So while you're doing panning, there's a lot of other things happening. You might want to sacrifice the graphics performance for application responsiveness. And then, so just to compare the last 2, so this is super sampling again, and the software anti-aliasing. Software anti-aliasing is still a lot better. So it's not quite as good, but it looks a lot better than not using anti-aliasing at all. So I think that takes me to the end of the maps talk, of the slides that I have prepared. But if anyone has any questions about maps, or now or later, please raise your hand.
So now you can put graphics cards in servers and stuff. Are you guys going to be moving to using like the WebGL version or some kind of OpenGL implementation to generate your maps, or are you going to keep like for the raster images that you send to the client, or are you going to keep using your software-based technique?
That's an interesting idea. I think GPUs are mostly designed for rendering things like on fly, like as fast as possible.
Mm-hmm.
Whereas when you're rendering a tile on a server side, you can take as much time as you want, and they're usually pre-computed.
Yeah, they're usually cached.
So we could take 300 milliseconds to render a tile and make it perfect. Add nice blurs or whatever, and we're going to continue using raster tiles for the future because we have many clients who can't support WebGL. iPhone, for instance, we're still serving up raster tiles for the map. So no, I think the answer would be no.
Okay, I'm just curious.
How do you manage the complexity between maintaining like the image version and the WebGL version? Is there a lot of shared things happening, or like if your team is the WebGL team, then like maps, the image team pushes a new thing and you have to like catch up, or is there a lot of sharing going on?
Yes, the answer is yes. There's a lot of sharing happening. So there's a big pipeline where they have we have a huge database of the world, everything in the world, every park, every tree, every building. These it's just kind of flat. There's no ordering to it. Things are just latitude, longitude. What is it? Where is it? And different versions of it over time. And they get converted into geographic tiles. So 4 tiles and 1 tile, and tree. next step is things are split up into different, basically bounding boxes of what's in that box in the world. And from there they get turned into images that have that stuff in it. Well, for us, we just cut it off at this point and send down that geometry to the client. So right before rendering, it's at the very last moment before rendering, that's where we stop it and put it into a wire format appropriate for the browser.